back into the ADC. We're going to be using that, setting that up this week in lab. Again, lab 4 is a 2-week lab, so we got a good amount of time to get that done. Where is my, here we go, PDF. So this is the ADC condensed ref. Also, you may want to glance at this before lab to kind of see what's all entailed in there. Just kind of showing you another picture here of the ADC. Remember I talked about the sample and hold circuit and then the converter itself. And we talked about how that does a little bit of a search algorithm to find you know, the actual value that's coming in on these. This is showing it with in what's called a differential mode of these pins here. There can be, if you put it in 16-bit mode, which I've never done. Again, that'd be something fun to play around with in your final project if you're interested. But in differential mode, one of the ADC ends is your high, one of the ADC ends is your low. And what that allows for is to reject a little bit more noise on your signal. And so anyway, well, in our case, really this is always ground, and we're just sampling, holding in an individual channel. It's called single-ended ADC. So a ground and a single input pin is what we'll be doing when we have this thing in 12-bit mode. Anyway, so but nice little picture. You can get. They do a good job of putting together some nice pictures of these devices. A lot involved here. So figuring out what all these parts are, it does take a little bit of time. I'm not expecting you to look at this picture. I look at this picture and don't understand a few of the things. So you know, pretty busy picture, but it is. They do take some time to look at that and to try to explain that to you. Okay, well, what we got to, we talked about last time how we've got this unit called ADC A, B, C, and D. So there are 4 of these units, in a sense, on our chip. And we have pins coming in from the outside world coming into each of these ADCs. Okay, so but we got to get some terminology down, and that'll help you out a lot in today's lab, this week's lab, is getting some of this terminology down. And then what we didn't get into last time was the scheduler, the sequencer of saying, hey, sample this pin, then that pin, then this one, and that's what's called these SOCs, start of conversions. Okay, a nice little picture of these is in there, what they call their round robin scheduling. Where's the nice picture here? Right here. So these SOCs. Okay, and so in other words, SOC 0 has got the highest priority. It's going to convert first, then SOC 1, then 2. There is, and again, we're not going to get into this, there's a way to actually divide these up and make SOC 0 through 3 the highest priority. That'll interrupt any other round robin, and it gets really confusing. But anyway, there are some neat features. We're not going to use those. We're going to just sample in order of this round robin, and we won't use all 16. We will just use, I think in lab we're only using 2 of these. So anyway, we need to talk about that. What is all going on here with the sequencer? So first, let's go talk about some terminology too, or what do we got in the labeling? Okay, we have again ADCA, ADCB, ADCC, and ADCD. Now let me go check here in the lab. Let's go to the lab here. And lab 4. I always forget what's connected to what here. Let me show you. So in our first part, we're going to be using these first, I think, 2 exercises. We're going to be using ADCD. ADCD. That's actually just the first exercise. And then in exercise 2, no, it is this first 2 exercises, sorry. Discrete filters. We'll be talking about filters too. And then the joystick, we're going to give you, actually that's funny that I brought this in today, we're going to, each of your board, you're going to have a little joystick like this. We're going to give you, these are little cheap joysticks. And these these analog inputs are already connected to ADCA. Set up ADCA like we did ADCD in the other examples. And then our microphone, which we'll be doing an exercise for this lab, is connected to ADCB. Just happened to be how I set it up. We could have done it a different way. There's no real reason for that. Okay, so we will be using those different ADCs. Then back to here. So then let's just talk about ADCD. But what I'm talking about here pertains to A, B, and C also. So inside ADCD, okay, there are input pins. So there's more than just one input. We talked about that last time, right? And it's multiplexed in, and then that's where our sequencer comes in. So inside ADCD, if you want to kind of make it a nice little compartment here, we've got then the pins that come into it. So pins ADC in D0 is how we're going to label that. ADC in D1, ADC in D2, and ADC in D3. And I could keep on. I have some problem when I think D3, I print B right away. I don't know. I've been doing that in my last class too. Anyway, we have this, but we actually have more. We have ADC in D4, D5. Those I do not believe, yes they do. They come out actually on this red board. Yeah, you can't really see it. You can put some really nice high fidelity BNC connectors on here, and it goes through a transceiver chip and all this kind of fun stuff. That again would use the differential capabilities of the ADCD. But again, we're not going to use those. Actually, we're only going to use in lab ADC D0 and D1, but you could sample all 4 of those, or you could sample all 6 of the in pins for D. Okay, so we've got all the pins that come in. We saw that last time a little bit, those pins. Go back to the data sheet. What pins could we bring in? Well, it's all the way up here at the top, right? For D, here are all our pins. ADC D0, 1, 2, 3, 4, 5, and then some of these other pins that are connected also to the other ADCs. This is kind of interesting. You can also sample your reference that the ADC is doing. Again, exactly, I'm sure there's some calibration reasons to be able to sample those signals. So anyway, but again, some things that I have, those features I haven't taken advantage of. All right, so we've got the pins coming in, great. And we're gonna consider those pins will have the in, right? We'll call ADC in, and then it's D is for the specific ADC. So we're gonna find that the joystick, I believe, is connected to ADC in A2, and in A3 is what our joystick is already connected to, okay? So we'll see that later in the lab. Great, so we got the pins. Next, and we're gonna get into interrupts today, just so because we're gonna be talking about this. So there are actually 4 interrupt sources from this ADC. That also, boy, you really have to think of something complicated to really need all those different ADC interrupts, in my mind. Because really, we just want to know when our conversion is all done. When our sequence of conversions is done, we get an interrupt. Well, again, I talked to you about how there can be some of the start of conversions can have higher priority than the other ones. So you possibly could use multiple interrupts. But, and unfortunately, I wish they wouldn't have labeled them this way. I wish they would put the int in there. But the ADC D1 is the first interrupt source, is how they label it in the data sheet. ADC D2, ADC D3, ADC D4. And at first glance, and I was tempted the first time I read through the data sheet, you would associate maybe ADC in D1 with this interrupt source ADC D1. Sorry, in D1, right, with D1, but it has nothing to do with that. This ADC interrupt is associated when the sequence is done. All right, so when the sequencer is done. And it just happens to be the first interrupt source. So it's a little confusing there. So we get that. Those are the 4 interrupts. We're just going to use ADC D1. So this is the one we're going to use. We're not going to be using the other interrupt sources. Okay? And then finally, each ADC, ADC A, B, C, and D, has 16 start of conversions. 0, SOC1, down through SOC15. Okay? I think I asked you in the how-to document of this lab, I asked you to use 4 of the start of conversions as a little question. Here, we're always, for this lab, we're only going to sample either 1 start of conversion or 2 start of conversions. Okay? Now, and you're going to see this as we march through the code in this lab. Each SOC, so let's divide it up here. SOC 0, what do you have to tell start of conversion 0, this element of our sequencer? Okay? You've got to tell it 3 things. Yes, you've got to tell it 3 things. 1 is which pin should it convert? Well, what do you think? What's the smartest pin to associate with SOC 0, do you think? When none of your pins have any priority. ADC in D0, right? But you can associate it with ADC in D3 if you'd like. They give you a lot of capability here in the sequencer, probably more than most people ever need when they're working with this ADC. Okay? So we have to associate it with a pin. We're going to do ADC D0 when we start out. That's great. We also have to associate it with a trigger. What event makes SOC 0 start converting? That is the trigger. We're going to see today that we're going to use EPWM5, and I'm going to come back to that. We're going to use a timer. We want this SOC 0 to happen at a periodic rate. We want to know, we want to sample our system every millisecond, or whatever I tell you to in the lab. Okay? So that's the trigger. Okay? And then finally, now this is not, you don't have to assign this, but what's associated with SOC 0 is what's called the result, and it's all caps, but the result 0 register. Okay? Whenever SOC's, whatever ADC pin it's associated with, whenever that conversion is done, the result is sitting in the actual converted value. And what is the result? It's a value between 0 and 4095. It's an integer. Where 0 volts, in our case, is, where 0 is 0 volts, and 4095 is our 3.0 volts. 3 volts is our range. And linear mapping in between them. So we've got this associated. And for, again, this makes sense to us that result 0 would have ADC in D0's result. That's nice. The numbers are matching right there. But what we're going to find when we get to ADC A and sampling the joystick, we're only going to sample pin A2, ADC in A, ADC in A2, and ADC in A3. So what we're going to do there, when we get to that exercise 3 of the lab, we're going to associate with SOC 0 the pin ADC in A2. So you'll be tempted to go look at the results 2 register, won't you? Because before it was matching with the 0 ADC in D0 matched with result 0, right? But there's no matching there. It's the result 0 is associated with start of conversion 0, and that can be any pin. See what I'm getting at here? Okay? So yes, it does get a little confusing. But we have that. And so each of these, and so in our case, we're just going to be using two. SOC1, its pin for exercise 1 and 2, we're going to associate that with ADC in D1. We're again going to trigger this with EPWM5, and its result will be in result 1 register. See what I'm getting at there? Okay. Now, what we'll do, again, we want a way to trigger all our entire sequence, let the sequence go. When the sequence is finished, we want to interrupt the CPU, right? That's our goal for all these exercises when it comes to sampling the ADC. Yes, I'll tell you in the lab we're going to use different sample rates to think about that. I think when we get to the microphone, we're going to sample it at first at 4 kilohertz, I think, or something like that, and then we go even faster, play around with different sample rates. But still, it all boils down to triggering, first setting up the SOCs, what pins they're going to sample, and then setting up the trigger for each of these. And then after the conversion is finished, we will jump to ADC interrupt D1, and inside that function, we'll read the 2 results registers, convert those to volts or whatever we do with it. Either take that microphone value and do some filtering of that signal and things like that. Okay, so that's kind of our flow here. And I'm going to repeat that again. We'll go through all the steps. But anyway, now what happens here? Notice we're going to trigger SOC0 also with EPWM5. Okay? You're going to see in the registers that we can... Okay, well then why did I choose EPWM5? Why would you use that to trigger, Dan? That's a PWM is a signal that we've been talking about that drives an H-bridge to drive a motor. It drives our LED to be bright. It drives our microphone to make a tone or whatever, right? So we're thinking PWM as an output signal, aren't we? Well, remember, there are 12 PWM devices in this. Remember, we used what we used in the lab. We used 2, 8, 9, and 12, didn't we? We used all those in the last lab, in lab 3. Well, there's a bunch that we didn't use. PWM3, PWM4, 5, whatever, 7, all sorts of them, right? And they're sitting there right now unused in the setup that I've created for our robot. Now, maybe you have an application where you need to use, in a sense, right, each PWM unit has 2 PWM signals, doesn't it? A and B. So maybe you would come up with a design that needs 24 PWM outputs. But boy, that sounds like a pretty complicated motor control driver or something, right? So more than likely, you have some PWMs when you do your design that you're not using for anything. So I've chosen, and 5 I've chosen not to use, except for just to use it as a timer, right? PWM5, or when we use PWM2, what did we do? We knew that the clock rate coming into the PWM was 50 megahertz. And we set it up so that it was in count up mode, and it would count up to the period value, which we set, if you remember in lab, at 2500 to make 20 kilohertz. So it'd count up to 2500 and then go back to 0, wouldn't it? That's just the life of that timer in there. Yes, it can generate an output signal, but it also can just be a timer. Okay? And so for that reason, this ADC unit allows you to trigger the timing of the ADC when you want it to convert with the PWMs, because they are, for the most part, timers. Now I could have chosen, and I've been fine too, I could have chosen to use CPU timer 0, CPU timer 1, and CPU timer 2. Remember? We've been using those, all 3 of those generate an interrupt right now, don't they? And we've got an interrupt function that's using them. And I could have chosen that, and probably would work great. You know, your labs, you could get by with just 1 or 2 timers probably writing your code. But I decided, you know, the PWM's not used for anything. The timers, maybe you could think about ways you could use all 3 of those in your design for your code. Anyway, but you could choose. You'll find when you're looking up, there's all sorts of different ways you can trigger the ADCs. You can even trigger them with external I/O pins. You can set an I/O pin as an input and have some signal from outside your chip tell your ADCs to start. Okay, maybe there would be some reason to do that. Okay. Anyway, so you'll see there'll be a big list because you're going to have to go down through the list and figure out what trigger EPWM5 is. There's a code for each of them. So, you know, 1 is some trigger, 2 is another trigger, etc. And you have to figure out what to set the trigger to so it is EPWM5. Okay, good. All right, now, as I said, we're triggering this EPWM5. This is the same event. What it means is when EPWM5 has reached its max value, period, its TB period value, and reset to 0, that's the event that triggers the SOCs. Now, we are triggering both at the same time. Once the 2 SOCs have been triggered, then that's where it falls to this round robin circle where the highest priority gets sampled first, the next priority gets sampled next, and so on in a round robin fashion. Okay? Of course, yeah, and it would go till the last one that you've got set up. In our case, it's not much of a circle. We're just going to sample SOC 0, then SOC 1, and then the round robin resets back to 0, waiting for the second trigger, the next trigger, right? And that's its life, okay? Once it triggers again, it samples SOC 0, SOC 1, goes back, waits for the next trigger, okay? So that's what we're doing. We're going to set up these 2 PWM trigger. SOC 0 is going to sample. When the sampling is done, the value will be stored to the results 0 register. Then this guy will be told to go next in our sequence. It will tell ADC in D0, for example, to sample, and the result will be sitting in result 1. Then, when both those, you're going to set up a register to say when the end, sorry, what's the best way to say this? So you have a choice. You can set this number to, in the register, you can set it to 0, 1, 2, 3, all the way up to 15. What is the name of the register? I probably should just do that. Let's see if I can find that. I better not. That'll take me too long. But anyway, it's in your ADC settings. You're going to say what SOC should cause okay, spit this out. When which SOC is finished should cause the interrupt is what I'm trying to spit out there. Okay? So you're going to set that register to 1. And when SOC 1 is finished converting, call interrupt ADC D1. Okay, that's the gist there. Okay, you could technically have the interrupt be called when SOC 0 is done converting, but then when you get into that interrupt function, SOC 1 may not necessarily have been finished already. So obviously you want to wait till the sequence is finished. Let SOC 0 convert, then SOC 1 convert, and then generate the interrupt. Okay, then we come into the interrupt. We're going to read the value of result 0 into a variable. Then in the interrupt, we're going to read the value of result 1 also into a variable. Okay? Then we can take that number between 0 and 4095 and convert it to a floating point number, which is in units of volts. Right? Between 0 and 3 volts. Now, in actuality, we're not going to connect anything to ADC in D1. We're only going to connect a signal to ADC in D0. which pin? Yeah, ADC in D0. It just happened to be what we're going to do. But I wanted to show you how to convert just more than one channel in this. So we're going to just work with one. I wanted to show you how to do multiples. The main reason we're only doing one is, we got one function generator that's going to generate our signal. We could bring that same function generator into 2 ADC ports or something like that, but just not worth the effort, right? But if later, when you get to the joystick, you'll see how to sample 2 things, right? The X and the Y of the joystick. So we will get to that in exercise 3, sampling 2 channels and actually using 2 channels. This is sample 2, but we'll only use 1. Okay, questions about this? A little confusing. Obviously, it's going to come a lot clearer when you start coding it up, okay? But hopefully that helps you to kind of divide up the different terminologies there. Now, let's look at what would be the next thing. Let me think here. We got to get into interrupts. So that's another part of this lab, is this idea of an interrupt, and get down a little bit deeper into what an interrupt is. Let me think here. Yeah, let's go ahead and do that. So we've got this now. All the different interrupts of the CPU. So if we go to the web lab, and up here at the top of the lab, you're going to see I referenced this table 3-2. Okay. So I'm going to zoom in a little bit. Here is this table that is listing off all the different interrupts that we can use on this processor. So there's quite a number, okay? And what we have, there's a little history here, unfortunately, and TI, their major customers is industry, Texas Instruments is. They tried to dabble in the cell phone market. They still do some of the supporting chips of cell phones, but the processor market in cell phones, they've dropped out of that in the last 10 years or so. So they're processors for industry, processors for cars, all that kind of stuff. That's their big business. And for that reason, and one of the reasons I think business likes them, is they try to be backwards compatible with their older processors, because we got an old processor that's working pretty well. We don't want to throw a wrench in the system to have to change it if we don't need to. Plus, then when we do want to update to the latest things, is some of our hand-written assembly code still portable type of thing. So they do try to stay somewhat backwards compatible. Well, and that's where this crazy table comes in, and this is where this idea of what's called the peripheral interrupt expansion, that's what PI stands there for. And again, for you guys, it's not super important that you understand all the details of why they did it this way. But the original C2000 chips only had, I believe, 12 interrupts. Okay? And yeah, exactly. So maybe even less than that. But here's these. So what you're going to see is you've got to enable, in the microcontroller, you've got to enable what's called the major interrupt. And that's going to be a number between 1 and 12 here. And that's these instructions you saw in the code. You maybe glanced at this as you were looking at the code earlier with other labs. Let's see, where's my code composer? So right here is the enabling of the major interrupt. Okay? And this was the old school. This was the early processors. This is all you had to do to enable the interrupts, but you only had 12 to work with. Okay? There wasn't a plethora of peripherals on the old chips. Okay? Couldn't do as much with the old chips. So this is what we'll call the major interrupt, and in that table, it's the left column. Okay. Then TI came up with this method to expand their interrupts. Where did I put it? So this table, so now when interrupt 1, right? To see that int 1 dot, right? Major interrupt 1 is associated with 16 minor interrupts, or whatever you want to call them. Okay? Again, we don't really need to understand this, and TI takes care of it for us in the C code that's generated. But when interrupt, for example, we're going to be working right here is our ADC D1. See that right there? ADC D1, we're going to call that interrupt 1.6. You see that there? There's a minor interrupt is the dot 6. So in a sense, well, what happens when you enable the PI, and again, your code takes care of this, not only, well, what the interrupt that happens is interrupt 1, legacy interrupt 1, and then legacy interrupt 1 knows to go, since it's dot 6, to go to the correct place to find the minor interrupt source code, the function that's associated with the minor interrupt. Anyway, all right, so that's why it's in this method. Instead of just listing off the interrupts, you know, what is this, 12 times 16, right? We could just list those interrupts 0 through whatever 12 times 16 is. Okay, instead they do this 1 dot, 8 dot, 9 dot, and all this kind of stuff to stay a little bit backwards compatible. Okay, so as I said in your code, we're going to first have to enable interrupt 1, and then we're also going to have to enable interrupt 1.6. And so a couple steps, and the lab walks you through that, and let me show you. You'll see here that what in the default code we already enable interrupt 1. Why? Because CPU timer 0 happens to be interrupt 1.7 that I need to enable. So go back to that table, and you'll see that interrupt 1.7 is timer 0. See that there? Okay. So the good news for you, right, for this week in lab, you simply just need to now what? You need to enable, so you'll have to say pi control regs dot, and now here's all the pi's, right? Here's all the major interrupts, 1, and then dot bit dot int 6, right? And you'll just have to set that to 1. So 2 steps. You got to make sure you've done this. What is IER? That's interrupt enable register. Okay, and that's the same. This pi, this is the peripheral interrupt expansion interrupt enable register. So you're enabling which interrupt is going to happen, right, by setting those bits to 1. All right. So those are the 2 steps to get things. Now, not only, it's pretty funny, not only do you have to enable the major interrupt, not only do you have to enable the minor interrupt, if you want to call it that way, you also, in your ADC setups, have to enable the ADC interrupt in your ADC-D system. And we'll, again, the code that we give you walks you through doing that. Okay, so getting all this interrupt stuff set up, it does take a couple things. And actually, there's one more step. We need to tell the processor what function to call when the ADC interrupt happens. Okay? To do that, we have to write to what's called the interrupt vector table. All right? And we're doing that also in this example code right up here. So for example, CPU timer 0, 1, etc. Right here, this is what we call the vector table of the processor. And we're saying when timer 0's interrupt happens, call this function. Recall that function, right? It's right down here, isn't it? You defined that function, oops, right here, didn't you? Or I gave it to you in the default code, didn't I? So this command right here is not calling the function. These right here, by setting the vector table, you're saying when this event occurs, when this interrupt occurs, that's where you should jump to in code. And that's what you should run. Okay? Good. And so we'll have to what we're going to have to do in lab this week for ADC D, for example, D1, we'll have to say pi vec table dot, and then there's a bunch of them here. We can find it's ADC D1 interrupt right here. Okay, so that's the one we want to use, and then that's going to be equal to whatever we call our function. You know, so Dan's ADC D ISR, interrupt service routine, is what that ISR stands for. Like that, whatever I called my function. Okay, good. Maybe you've also noticed this. So a lot of little steps here. Maybe you also noticed this. Look at how the interrupt functions are defined. Like here's timer 0. It's got this interrupt underscore underscore interrupt in front of it. Okay? That is telling the compiler this is a special function. Okay? So let's think about what's going on there when an interrupt happens and try to get below a little bit of what we've been calling magic, right? And again, we may not get through this as in much detail as you want. If you want to sit down and talk a little bit more about it, we can. But again, in the CPU, let's try to draw this. Okay, so here's our 28379D 9D processor, right? Okay, then we've got the memory inside this guy. And part of this memory, a little chunk of it, is this thing called the vector table. So let's expand that out, this vector table. And each little spot, I think it's every 32 bits, it could be every 16, but I believe it's every 32 bits. In this place, each spot on this vector table are associated with a different interrupt. Okay? So those interrupts, again, are what we saw in the table. So each of these interrupts, EQEP2's interrupt, the serial ports interrupts, all those are associated with a different spot in this vector table. So vector table. And by doing that assignment, saying that vector table element equals ampersand, the name of your function. What's ampersand mean? It means the address of, right? Ampersand in front of a variable means give me the address of where that's located. So if you put an ampersand in front of a function, it's saying give me the location of where that function is located in RAM. Yeah?
So it's similar to passing by reference?
Exactly. When you pass a variable by reference to a function, you're assigning, the reference means you're taking the address of that variable and assigning to the local variable that is a pointer in your function. Okay? So in this case, you're actually writing the address where your function is located in memory to this place in RAM, to this vector table. Okay? And TI, when they built this chip, they associated each of these spots with an individual interrupt. Okay, so there is a unique spot on the vector table for every one of these interrupt sources right here. Okay, and so you could assign a function to all of these if you wanted to. That'd be a crazy application if you used every interrupt on this processor, but there would be a way to do that. Also, another interesting thing, if you look here, TI does this for us. And some of you will probably run into this because it's fine that you missed a step. There is a C file right here called default ISR. TI for us goes through every interrupt and assigns a default function for every one of the interrupts. So, you know, somewhere there's just a load of them here. I2C interrupt, I2C FIFO interrupt. What does these default functions do? They simply, if for some reason you accidentally cause this interrupt to happen in your code without assigning your function name to it, it'll come to this function, and they're right here. Assembler eStop is like a breakpoint. It'll never get past this line of code right here. So if you're running your code in Code Composer and it happens to stop at an e-stop line of code, you probably have not set up that interrupt with your function. It's using the default interrupt function. Okay? So that's something to keep in mind. But anyway, and then you just think, oh shucks, I forgot to set up the interrupt for ADC, for the transmit interrupt of the serial port C or whatever, right? And you say, oh crap, that's right. We got to go assign it to my function. Okay. Also notice that every one of these functions has type interrupt. Okay. So what's going on there? When an interrupt function happens, a little bit of hand waving here, what's exactly going on, but so when an interrupt happens, you've assigned this spot in memory, and this is for maybe your ADC D1. Oh my gosh. ADC D1. And you put in here ampersand the address. It'll be a number, of course, right here. The address number of Dan's, I'm just going to abbreviate it, Dan's ISR. Okay? So that's what's sitting there at that spot. So you're going along. The main place we'll be when we get interrupted is that while loop, printing the tera term, right? So we're sitting there spinning in the while loop, and 1 millisecond's gone by. So boom, you get the interrupt. Well, actually 1 millisecond's go by, so you go tell the ADC to start converting. When the conversion, those two conversions are done, then an interrupt's generated, right? That's actually what happens. And so that at that moment in time, what happens is, that's why we call it a hardware interrupt. In hardware, the CPU knows to go and look at this immediately. Okay? It knows to change. There's a register in the computer called the program counter, PC. That's where you're currently at in memory in your program. You're marching through the assembly instructions. Boom, boom, boom. The instructions that were generated from our C code. So we go this line and this and this, and we have a jump, we go over here, or whatever. Well, that program counter, whenever that interrupt occurs, it knows, because it's ADC D1's interrupt, it knows to jump to that place in the interrupt vector table, the program counter. And then, when it sees where that memory location is for your function, the program counter then jumps to your function and starts marching through that code. All right, well, the problem with that interrupt is, okay, so again, we have our while loop code, while 1, and serial print inside there, for example, printf. Well, this code right here, it uses, so how does a CPU run code? Well, remember, it's all these assembly language instructions that convert to opcodes. And those opcodes use the internal registers of the ALU to add things together, to check if something's greater than something or whatever. So it's got a status, or what we call the context of the processor. What are all its registers set to? Okay? Well, when an interrupt function is called, C does this for you. It saves the context of your processor. Or we could call it save the state. So it takes whatever the processor's mode is, wherever it is, whatever code it's doing, it takes that and shoves it out to the stack of memory. In your C program, you have to allocate a chunk of memory called the stack. So the interrupt function is called, the first thing it does is it saves the context of the processor to the stack. Okay? Then it actually runs your code. So by putting underscore interrupt as the type of your function, the C compiler does this automatically for you. Okay? So the while loop was halted, but we've saved the state of the while loop code in RAM, in stack. Okay, then our code can start running, march through it, right? Whatever we're doing. Read those values of the results registers, convert it to volts, write the value back out to our digital to analog converter, all that great stuff. Then when it's done, again, because we called the function type interrupt, the C compiler knows to go grab that stuff set up on the stack, put it back to all the registers, and then jump back to where we interrupted the while loop, for example, or whatever got interrupted. So then the guy over there, the code over there doesn't feel like anything changed, did it? It's wherever it was, its state was saved. After the interrupt's done, it restores that state, and then you're back to doing the while loop. So that's how it can interrupt your lower priority code. Okay? And again, it's all this scheduling of that is all done in hardware. Done with this table lookup of the interrupt vector table and etc. Okay? That's a little, it still sounds like a lot of magic, doesn't it? Right? If you really wanted to learn how that all worked and what to say, what is the context of a processor, you'd want to go write it all in assembly. And you wrote that all in assembly, you would have to do your own stuff. Actually, too, TI documents this. TI, if you go to its C compiler or its assembler coding documents for this processor, it would tell you exactly what all needs to be saved in the processor when you did this. So it's not like you would have to figure out what needs to be saved. This is all documented in any processor, what registers need to be saved when you do an interrupt like that. Okay? All right. Excellent.